The question that I have is, could you do a 1D consolidation example? I have a clay layer, total thickness 15 feet, is sandwiched between two sand layers like this. This clay layer is found to have a very thin sand seam within it. The sand seam is 10 feet from the top of the clay layer. What does that do? Well, it introduces a drainage boundary inside the clay layer. So now you have two doubly drained clay layers, the top 10-foot part and the bottom 5-foot part. The question is to find little t50. More precisely, what is the time that it's going to take before this happens? In other words, the total settlement of the 10-foot layer and the 5-foot layer divided by the total ultimate settlement of the 10-foot layer and the 5-foot layer to become equal to 0.5. So individually, the degree of consolidation for each layer may not be 50%. From the definition of the average degree of consolidation, the average degree of consolidation for the 10-foot layer can be written like this, and the 5-foot layer can be written like this, right? So now I'm going to evaluate S10 and S5 from these equations in terms of U10 and U5 respectively, and put them in this equation in order to get this equation. To understand the structure of equation for the ultimate settlement, I'm going to utilize this equation right here. So using this equation, we can write down S10 to infinity as this, mv times the change in vertical stress multiplied by the thickness of that layer, which is 10 feet. And S5 infinity can be written like this. So from the two, you can see this ratio is simply 10 over 10 plus 5, which is 2/3. And similarly, this ratio is 1/3. So now I'm going to take these numbers and put them over here. All right. And then equation 2 becomes something like this. There are two ways to proceed from here. First, let's utilize this approximate equation. We know the approximate equation is valid only as long as the average degree of consolidation is less than 60%, right? So let's substitute the components of this equation here and expand it and set that to 0.5, and that equation can be solved directly for little t50. And when I did that, I got 27.6 days out of that. Then I calculated U10 and U5 individually. U10 worked out to be 37.5%, which is less than 60%, so we are okay there. But unfortunately, U5 works out to be 75%, which is greater than 0.6%. Although it's pretty close, it's not, strictly speaking, the approximate equation is not valid. The second approach is iterative approach. All right, I simplified T10 and T5, capital T10 and then capital T5 in terms of little t50, and we get these equations. So here I have a table, all right? So basically, I'm going to pick a value of little t50 and calculate my big T10, big T5, and from that, I'm going to utilize this chart here, which is supposed to be accurate, and calculate my big U10 and big U5, and from that, I'm going to find 2/3 of U10 plus 1/3 of U5, which we will call Y for now. We know Y is supposed to be 0.5, right? So the idea here is that you try different values for T50 and see if you get a value of 0.5 on the last column here. So I tried two numbers here. We know we have an approximate idea. The approximate method gave us 26.7 days, right? 27.6 days, right? So I tried a number below and a number above, and it turns out that when I tried 30 days for T50, y works out to be 0.493, which is pretty close to 0.5. So little T50 by this iterative method is about 30 days, which is pretty close to what we got earlier.